Hello and welcome to this, the fifth in a series of talks by members of the Resource Use Institute. The Institute was established in Scotland in 1969 to highlight fresh approaches to the use of resources to meet economic and environmental challenges. The series covers various aspects of resource management, land use, community regeneration, minerals, the environment, and energy. And a number of those elements come together in this evening's session. It's presented by David Boyd, who's an engineer, and looking at an issue that's important to engineers, challenging to engineers, important to all of us. This is the question of hydrogen and its role as the possible fuel of the future. Well, it's being very much spoken about as that, and there's projections that by 2030, it might be turning over up to 80 billion euros a year. That's an EU prediction, and various other countries around the world are making similar predictions of the role of hydrogen in the future. Well, that's the theory, but what about the practical challenges and the practical steps? It's a fast changing situation, and this evening David's going to look at challenges, asking about solutions and questions. Will it simply reinforce problems of energy costs, or could hydrogen be developed as a means for alleviating fuel poverty in rural Scotland? Well, David's the right person to ask these questions. He's a highly experienced engineer, a senior manager with expertise in nuclear, civil and geotechnical engineering. He's also expertise in systems management and business development, and that's come from more than 40 years of working with major engineering consultants. David's turning his focus then on hydrogen, and David, it's welcome and over to you.
Okay, thank you, Harry. So I think you can all see the screen. It says, not an expert overview of a green hydrogen future. So I'll just move on. We start with a bit of prelude. This is something from a book by Edward de Bono, which he talks about different ways of understanding things. There's a simple description. You plug it in, switch it on, and it works. There are porridge words, as he calls them: renewable energy, green hydrogen, carbon free, and things, and magic, you know, just words that are just sort of general. And then there's more specific, moving on from that to electrolysis, pressurized storage, fuel cell, you know, something that you've got a real name to it. Then onto even more complicated is the way it works. And finally, to full details, all the physics of how things work. Well, this talk is set at level 3-ish, and definitely not level 5. So it's not an expert view. So it's when you see these words, electrolysis and pressurized storage and stuff, don't really ask me the full details of how proton exchange membranes work, because I don't know. Just a little bit about sustainability. Sustainable projects make things better today. If they don't make things better today, then why would you do them? And you have to do it efficiently, and you have to bank for the future. So doing something today that makes things better in the future is the banking for the future. And the final one, the four, which is with fairness, because without fairness in the system, people eventually withdraw their support and projects become unsustainable, or governments become unsustainable. So just moving on a bit, here we are now. The hydrogen industry is going crazy. There's so much going on. Every day there's a new announcement about something to do with hydrogen. The EU is committed to produce 10 million tons of renewable hydrogen by 2030. And that translates to about 80 billion euros. It's a huge, huge market, potentially. Scottish Power's committed to producing something called a hydrogen hub in the Cromarty Firth, and there'll be more of these in Scotland. European gas network operators want to create a backbone pipeline network so that they can pump hydrogen all around Europe, and as a forerunner to a trading mechanism. SSE have proposed to build a hydrogen production plant at Brora attached to an existing wind farm. And SGN and INEOS are going to, that's Scottish Gas Networks, are going to trial a hydrogen pipeline in Grangemouth. There are existing hydrogen pipelines in other parts of the world. So, you know, having a hydrogen pipeline is not that unusual, but of course, the stuff leaks. So you have to make a leak-proof pipeline. This diagram appears later as well. And this shows hydrogen in the middle here, with green power over here from hydro, solar, wind, feeding into an electrolyser that produces hydrogen. And then the hydrogen goes out to industry, to chemical industries like ammonia and fertilizers for agriculture. It goes into the petrochemical industry, which is a principal consumer of hydrogen at present. And it goes into transportation for road, rail, marine, aviation, possibly. And right up the top here to heat and cold for domestic use. So you see this again. So the contents of the presentation are background, production, how do you make it, use, what would you use it for, how do you store it, how do you move it about, safety is a big issue, and then something about the politics and strategies for a hydrogen future. So the background, hydrolysis was discovered at the time of the French Revolution. So it's been around for a long time. Hydrolysis coupled to renewable energy gives you green hydrogen. There is blue hydrogen and gray hydrogen. Blue hydrogen is made from hydrocarbons and coupled to carbon capture and storage, and gray hydrogen isn't, it's the other stuff. It's been much talked about as an industry for at least the past 30 years, including in Jane's book on with Markham Slessor, where she's got a whole section on potential for hydrogen. There's been hydrogen fuel cells to produce electricity and heat for some time. There's also a hydrogen internal combustion engine, so it burns hydrogen rather than petrol. Hydrogen power stations are available, which are gas turbines with a combined cycle. So you have a steam turbine at the back of a gas turbine. There's currently a lot of interest in co-burning hydrogen with natural gas. That is enhancing the calorific content of natural gas with hydrogen. There's been talk of a hydrogen city, which has got a ring main around it, which has hydrogen in it, and you plug into the ring main and run your domestic appliances. There's hydrogen vehicles, and there are already quite a lot of hydrogen vehicles around, particularly heavy vehicles like buses and lorries and all sorts of commercial vehicles, and ships and other heavy machinery. One of the problems that you have with hydrogen and steel is the potential for hydrogen embrittlement. And this is one of those things that you say, is it really a problem or not? But it's certainly one thing that has to be looked at. And of course, it has a propensity to catch fire and go bang. So that's a real fear for people. And here's why. This is the hydrogen airship that caught fire in 1937. And people will cite this as saying why you can't have hydrogen, because you're going to have disasters like this. More recently, there have been other disasters with hydrogen. At the Fukushima nuclear power station in Japan, there was a hydrogen explosion. Hydrogen was produced in the reactor by a malfunction, which blew the top off the reactor. And even relatively small scale things, there's something called a hydrogen road in Norway, where there are hydrogen fuel stations for vehicles along this road. And one of them here caught fire. Now, this is very interesting because this hydrogen fuel station makes its own hydrogen. There's a wind farm in the next field, and there's an electrolyser which makes its own hydrogen, and the hydrogen then goes into somebody's car who pulls up here. Very interesting. But it was a valve that went. So these connections between one bit of the system and another are quite susceptible to leaks, as you would expect if you were going to have, if you had one pipeline, one piece of pipe joining another, it's the bit where they join where you're likely to get the problem. So there's been a lot of research and development on different types of joints. That's ongoing, but that's what happens if you don't deal with that. So here's an interesting but quite a busy slide about the properties of hydrogen. It's the smallest atom, the lightest, it's highly diffusive, and as you saw above, it's highly flammable. At 1 bar and 25 degrees C, so that's ambient temperature, it doesn't weigh anything. You know, it's light as anything. It's much, much lighter than air. If you have a kilogram of hydrogen, you've only got a few grams of the stuff in there. The mass energy content, though, is 120 megajoules per kilogram, and which is higher than methane and higher than petrol per kilogram. But of course, if you've just got gas, you don't have very many kilograms. So this is what this volumetric energy content is. It's only got 11 megajoules per cubic meter, where methane has got 40. So because methane is denser and has got less energy content per kilogram, it works out that it's 4 times for the volume at ambient conditions. It's got 4 times the energy than hydrogen has. But at 700 bar and 25 degrees C, so that's compressed into a vehicle tank, and they are seriously looking at 700 bars, which is massive. The density goes up to 39, and the volumetric energy content therefore goes up to 4,500 megajoules per cubic meter. So when it's compressed, it's got a heck of a lot more energy per cubic meter than not compressed. And if you can liquefy it, which means taking it to minus 253 degrees C, you get up to 71 kilograms per cubic meter, which still isn't very much. Because remember, water is 1,000 kilograms per cubic meter. And LNG here, as you see shown, is 450 kilograms per cubic meter. So the volumetric energy content of liquid hydrogen is a lot less than the volumetric energy content of liquefied natural gas. Just going on to this last one, which is a kilogram of hydrogen is equivalent to about a gallon of petrol, 4.5 litres. And a car goes about 80 kilometers on 1 kilogram, and would cost, therefore, about £8 or £9 in petrol. Now, a kilogram of hydrogen is equivalent to about 33 kilowatt hours of electricity. So, in electric, if you look at domestic electric costs, it's about you would have to pay £13 or so to get the equivalent of 1 kilogram of hydrogen. And the cost of hydrogen at fuel stations in Germany is about 10 euros per kilogram, which is about £8 or so. So these are just a few little figures that we can come back to if somebody wants to ask a question. But the number of zeros in the equation, and the kilograms, and the terawatt hours, and the 10 million tons, the number of zeros can be quite confusing, and you've got to go back and do your maths if you want to know what these figures really mean in terms of the quantity of hydrogen that people are talking about. So back to that hydrogen future. We've been through this before, and it's just stuck in again. And now we're going to be going on to how you make it through electrolyzers and what you do with it. So production and uses. Water hydrolysis, that is passing electric current through water, produces oxygen at the anode and hydrogen at the cathode, and this is what's called green hydrogen. They also produce it from methane pyrolysis. That's methane is bubbled through molten metal, and it breaks down and produces hydrogen. The most common way of producing it, though, is through steam reforming with methane at high temperature, and that produces grey hydrogen, which can become blue hydrogen if you've got carbon capture and storage. Oh, sorry, let me go back. And there are other methods. So currently, the world production of hydrogen from all methods is about 90 million tons per year. So an EU proposal to produce 10 million tons a year is a significant part of the world production at present. It's used mostly in the petrochemical industry for the desulfurization of hydrocarbons. And it's used to make ammonia, which is used to make fertiliser, and it's used for fats and oils, and even in margarine. It's used in the semiconductor industry as rocket propellant and all sorts of other special scientific-like uses. And it's used as an energy carrier in fuel cells and enhanced fuels. So here's what it looks like. Here's what the world production looks like, and what the International Energy Association say or forecast is going to happen. In 2020, it's mostly industry and refining. And in 2025, they say that there's basically going to be an introduction of grid injection. Whether this happens or not is another thing. And then by the time you get to 2030, you've got a large amount of grid injection, or whether they mean domestic use, I don't know. But you're also looking at uses in buildings and in synthetic fuels, growth of ammonia as a fuel. I'll come on to that in a minute. And then growth of hydrogen in the transport sector. So that's a prediction that you're going to go from 90 to 210 or something by 2030. That's a heck of a growth. So let's just go on to production. How do you make it? Well, there's alkaline electrolysis that's been known about for years, which is, well, you'll see a slide in a minute, but it's an electrolyte and a cathode and an anode. You pass electricity through it, you get oxygen at one and hydrogen at the other. There's something called a proton exchange membrane, which is a relatively recent development, but it's now become commercially available, widely commercially available. And there's another diagram coming up. But this is the sort of VHS of hydrogen production. the proton exchange membrane method has taken over from these other methods. So there's no more Sony system for making whatever it was that they made that didn't become VHS. I can't remember what it's called. But following along is this stuff called solid oxide electrolysis, which might become the DVD of hydrogen production. It's got some good credentials. And then there's a whole host of other methods that are coming along, and all in research and development, but they're developing fast. But this proton exchange membrane method seems to have got the jump on everything else. So alkaline electrolysis. This is the liquid method, using usually potassium or sodium hydroxide as your electrolyte. You have a cathode and an anode, and you have some sort of separator so that the bubbles don't mix again. And you introduce water, and what you get out at this side is hydrogen, and what you get out at this side is oxygen. And that's a liquid, low temperature liquid process. And that was the preferred approach for years and years, until they came up with this proton exchange membrane method. And this is a plastic sheet. On one side, in fact on both sides, but different metals, are catalysts, which become the anode and cathode. You introduce water at relatively low temperature, and this proton exchange membrane allows hydrogen to go, hydrogen ions to go through, but it doesn't let electricity through. So you produce hydrogen at one side, then oxygen at the other side. And this technology is now becoming widely available. And Siemens, for instance, have just built a very large factory to produce cells that do this in Berlin. And there's a very large manufacturer of these types of membranes in Sheffield. The one that might be coming along, the sort of DVD that's going to replace the proton exchange membrane, possibly, but needs to run at high temperature, but has got possibly higher efficiencies, is this solid oxide electrolysis method. The great advantage of this is that the cathodes and anodes don't have to be platinum or palladium or other noble metals. They can be a more affordable material, and the stuff comes in as steam. It's high temperature, and this is the sort of method for producing hydrogen that they've been looking at in the nuclear industry for linking up to nuclear power stations, where you've got the opportunity for high temperature steam as well. This is a busy slide, which you can look at another time if you download the presentation. And this looks at some of the differences between the different methodologies. The membrane method is 50 to 80 degrees C. Solid oxide is 700 degrees C. So you finish up with a different type of development altogether. So the electrolyser is in the middle of this here, but that's not all that's involved in a system. You have all your you need electricity coming in. You've got to rectify that to direct current. So if this comes in as AC, it's got to become DC. You've got your electrolyser in here, which produces oxygen, and you need to collect the oxygen from the water and then take that to whatever you're going to do with it. And on the other side, You have to do the same thing with hydrogen. There are various condensates that produce, and then you need a gas reservoir, and there's a whole series of things that are needed, dryers, etc., before you get hydrogen. So that bit there is only part of the system. And here's a very interesting diagram, because this shows the breakdown of a system for a 1 megawatt proton exchange membrane system. This is from Siemens. And the whole system, the electrolyzer system, is this. The balance of plant, that's all the buildings and earthworks and goodness knows what, is 55%, or say half of the cost of the project is the balance of plant. The stack that you're talking about in here has got the membranes, the stack assembly, which is an end plates, which is one of these here. It's one of these things. That's not very expensive. The membranes themselves make up a quarter of the cost of the stack. And when you go back down further, the membranes, you've got manufacturing, you've got the different electrodes and catalysts that are needed. So the membrane is something like a quarter of half of the total cost of the project. And of course, these will change because every project is going to be different, but that's an indication. Just this bit here can be built by practically any engineering contractor. So there's plenty of work there for the regular industry. You don't have to be a specialist. This stuff here is very specialist, but the balance of plant, the buildings, and etc. There's still a lot of work that can be done by others. Now we come to one of the problems: is when you've produced it, what do you do with it? How do you store it? This is a slide which I picked up from a conference in Edinburgh, in Glasgow recently. The scale's a little bit weird because it goes 1, 1,000, 100,000, and then a million. So in fact, it's more than a million, isn't it? Because that would be a gigawatt. So that's a very large number. And this is attempting to show the different ranges of how you can store stuff. And I'll say something in a minute about solid state, but you can attach hydrogen to other materials and then free the hydrogen from it later. But that can only work at relatively small quantities. Pipelines, if you have enough of them, you can store a lot of stuff in your pipeline. Vessels, that's different types of tank. Liquid carriers, which are both liquid hydrogen and other forms of liquid that are produced from it. You can store it as ammonia, for instance. So they're relatively high volumes. And then there are these things: salt caverns, hydrocarbon reservoirs, saline aquifers, which are really there for storing quantities equivalent to a season. So, or a year's worth of hydrogen. So these, 30 million tons might be able to be stored in an aquifer, but that's an enormous amount. So I'll just go on a bit. So here's the storage technologies: low pressure gas in tanks and pipelines. Obviously, these are just ordinary tanks that you'd see. High pressure tanks in special tanks, because high pressure 700 bar is massive pressure. So the tanks have got to be very, very robust. Liquefied gas, of course, needs cryogenic tanks. Large quantities can go in these, as we've just said. Metal hydrides, ammonia, and then there's other R&D going on. So there's quite a lot of work going on about storage technologies. So here's a couple of pictures, some low pressure gas in tanks, which you know, you can imagine as being fairly conventional. This isn't a great picture, but it talks about the complexity of compressed fuel storage tanks. These are the sorts of things that you would have in a bus or in your car, and they're impact resistant. They've got special valving, they're multi-layered, a carbon fiber reinforced shell, and probably a polymer inside here. And so that's a pretty specialist piece of kit, as is a liquefied gas tank, because that's insulated and gas can bubble off. And of course, when it bubbles off, it takes in energy and cools. And so again, that's a pretty sophisticated piece of equipment. And as I said, in large quantities, you can store it in rock and salt caverns. And they've already been doing this for years and years at ICI, at Teesside, in some salt caverns. And in France, they've been storing hydrogen in porous rock. And there's talk of using, sorry, I'll go back. There's talk of using depleted oil and gas fields. And then this issue here, which is cushion gas. So that's, if you put it in there, when you take the gas out, you have to leave some there as a cushion. And I'm not sure I understand that, but it becomes quite a problem at large quantities and in these sorts of places. And as I said, there's solid state storage as metal hydrides in porous medium. And then there's some R&D into various types of carbon-based materials that can hold hydrogen. I'm not sure I understand all this. It's a bit too much chemistry for me, but it's certainly an area for sort of specialist storage of hydrogen. So what do you do if you use it? Well, how would you use it? Well, it can be used for heat and power, for civic buildings, schools, hospitals, farms, commercial kitchens. And there you would use fuel cell technology or direct combustion. Now, a fuel cell is the reverse of the PEM, of the proton membranes. It's you introduce oxygen, that's air at one side, and you introduce hydrogen at the other side. The hydrogen goes through the gap, goes through the membrane, creates oxygen, and in so doing, drives an electric current between the electrodes. So that's how a fuel cell works, and it produces electricity, but it also produces heat. So you can have a fuel cell in a container next to your hotel that will provide the electricity and the heat for the hotel, or a couple of containers with this stuff in it. As I said at the start, it's future use in heavy vehicles and buses and ships and cars and possibly airplanes. And again, this is fuel cells and internal combustion engines. So you might have ships running on internal combustion engines that are burning hydrogen. There's domestic use for heat and power, cooking and house boilers. And again, that's fuel cell technology and direct combustion through special burners attached to either the cooking equipment or to the boiler. And there's lots of use in industrial. Sorry, I didn't mean to do that. Green hydrogen to displace grey hydrogen in ammonia for making fertiliser, etc. And there's this particular project which I've noted here, which is a joint venture between Swedish steel producers and Vattenfall, the Swedish utility, called Hybrid, which is a world-breaking initiative to use hydrogen in the steel industry. And of course, you can use it for power in the heat and power in the water industry, and you can use it for synthetic fuels. And you can use it directly for power through hydrogen power stations, which are useful for balancing variable renewables in combined cycle gas turbines and leading on to direct district heating. So the power side of things is a future use. And of course, all these, when you produce it, you produce oxygen as a byproduct, which you can either vent, or you might be able to use it for something. I don't know what, but it's been talked about as being fed into fish farms to increase the productivity of fish and reduce the harmful effects of pollution. So let's go on to ammonia. Well, ammonia is hydrogen, nitrogen. It's the other way around. That's 1 nitrogen to 3 hydrogens. Sorry, that's an error. The nitrogen comes from the air. You produce this liquid, and then you ship the liquid. And you can store the liquid in tanks. They've been storing ammonia for ages, for years and years. And you then turn your ammonia into fertiliser and other industrial chemicals, and it's relatively safe. And then at the other end, when you've got your nitrogen, when you've got your ammonia, you can break it back to hydrogen and nitrogen. It needs some more energy going in, but the round trip gives you an efficiency that looks as if it's viable. But ammonia is also a fuel, and you can burn it in internal combustion engines. And there's been a lot of interest in using ammonia as a fuel for ships. And this little site here that I've cited talks about speedboats. And at this conference in Glasgow that I went to a few weeks ago, there was an ammonia speedboat, ammonia-powered speedboat, which looked as if it was something that Batman would drive. It was a fantastic-looking machine, and it burnt ammonia. Now, the problem with ammonia in an internal combustion engine is that it's a much slower and higher. It needs a higher temperature to burn than petrol. So it doesn't really work very efficiently unless it's in slow-moving internal combustion engines, like ships' engines. Okay, I'm just going to move on to some other terminology that's emerging. These terms of pods, hubs, and valleys. I think I've probably invented the term pod, because this is where green hydrogen is produced, and it may be used locally or exported or collected and then moved on to somewhere else. And a pod at present would be the proposed development at Brora, and the quite extensive developments on Orkney, and it doesn't count small dedicated production units which might come up. But I could imagine there being 100 plus, maybe 200 pods around the UK where there is abundant green energy. Now, hubs are centres for hydrogen collection, storage, and onward transmission, and they may include a pod or two, and some local usage. But you might get new industry using hydrogen, such as making ammonia. And I could see that there might be half a dozen of these in the UK, perhaps half a dozen in Scotland, and perhaps 20 in the UK. And these become the key to export. So if you're going to have a hub, you would bring the stuff into your hub and you'd have an export terminal there of some sort. Now, the next one down are valleys. There's been talk of there being hydrogen valleys in Europe particularly. So this would be where the hydrogen comes into Rotterdam or comes into Hamburg or somewhere, and then is distributed from there to other uses around the area. And these would be close to the centers of population, base for larger scale storage, distribution, perhaps power stations, new industrial usage, etc. And you could see that the Forth Valley or central Scotland might become a hydrogen valley, Teesside, Humber, Thames, South Coast, Severn Estuary, Wirral, Belfast, and in Europe. But there won't be huge numbers of these. It won't be every valley is a valley. These would be some sort of collection of industrial, it would be an industrial area for the reception of hydrogen. Now, these are likely to develop in parallel to pods first. And basically, there is no export from hubs until there's a valley to receive it. So there's been a new development between the Scottish government wanting to export hydrogen to Germany. So it would export from a hub yet to be created to a valley yet to be created in Germany. But that idea of there being a hub exporting to a valley is growing legs every day. And this export to the EU, etc., by pipeline that may be possible, although a pipeline from Scotland to Germany is a hell of a long way, or by sea, either as pressurized gas or as liquid gas, and then worldwide. So there's a lot of questions around this whole area of how do you move the stuff around. So this is my next one, which is industrial supply, which is pods to hubs to valleys. Pods to hubs can be perhaps a short pipeline or tankers. Hubs to valleys, some sort of specialist dedicated pipeline, either a new submarine pipeline, which would be much cheaper than an onshore pipeline, or possibly repurposed gas pipelines, although I'm not convinced about that. Oh, sorry, I did it again. You could ship it as ammonia, or you could ship it using new ships to new terminals and new storage facilities. And this is a picture of the world's first liquid hydrogen carrier. It's got a tank of 1,250 cubic meters, which is not that big, and it only carries 88 tons of hydrogen. And it caught fire a few weeks ago. So, and the fire came from one of these connections between one bit of pipe and another bit of pipe. So this whole question of connections and valves is an ongoing challenge for safety. Domestic supply, and I say domestic because it's the sort of thing where natural gas would go now. There's a lot of talk and a lot of proposals from the gas companies with vested interest that they should blend it with natural gas and deliver via the existing gas network with a large amount of storage in the pipes themselves. But the feasibility is not yet fully proven. But old town gas supply included a lot more hydrogen. Got a high hydrogen content. So there's some feasibility in there, but how it works is being developed. You could build dedicated pipelines, and there are some dedicated hydrogen pipelines over long distances in the United States. But the best technology is still a subject for R&D, and they'll be costly onshore and cheaper offshore. And then, of course, if you're onshore, you've got all the planning and safety issues. And I'd like to run a new hydrogen pipeline through the center of Stirling, and you'll have everybody saying it's not safe because of the photograph of the Hindenburg disaster. So there's a lot of issues about new pipelines. And there's a huge difficulties, mega difficulties of the transition. If you want to burn hydrogen, you've got to change all the burners on your cookers and your boilers. You might need new appliances. And then there's the question of how to switch from a natural gas network without a dedicated pipeline as a replacement. Becomes very difficult to see how you could just switch from what we've got now to burning hydrogen. But I think there's a great benefit to by tanker to domestic storage tanks. And I call this the Calagas solution because the technology exists. They've got tankers now, pressurized tankers with a delivery nozzle that can come along and can fill up your storage tank if you've got one, and or if it's a shared one with neighbors. And I think this is a very good option for rural areas. Safety and regulation. Well, this is a big bugbear, but there's lots being done on this. The whole industry is going mad trying to work out it moved from existing safety standards for hydrogen, which are used in the oil industry, to produce new standards for the production plant, for pipelines, for domestic appliances, tanks and tankers, fittings and valves, etc. And there's a big need here for a whole series of training in what is the standard, what you have to do to make sure that all these things don't blow up in your face, literally. And then there's the regulation. Oh, sorry, I've done it again. Let me go back. Regulation. So associated with this is there's likely to be a new program of legislation. And that might take donkeys, because you know what legislation's like. And there's likely to need to be a regulating body. That's a safety regulator, might be part of the health and safety executive. So I think that on safety and regulation, there's a way to go yet, but it's something that lots is being done on that. Right, I'm coming on to costs. As I said at the start, the cost of hydrogen in Germany is about £8 a kilogram, but I think it's matched to the cost of petrol. So it might not be a real cost. It might be subsidized in some way, but I haven't found that out. The US are targeting $1 a kilogram for production of hydrogen. It's still a long way away from that. They're about $5 a kilogram at the cheapest. But if you look at what is a lot more likely, it depends on the cost of renewable energy. And renewable energy is probably coming in at about £100 per megawatt hour. That's 10p per kilowatt hour. And might be less than that now. It might be 8p, 5p, something like that. But that's still something like £2 or £3 a kilogram for, of hydrogen equivalent. And of course, if you have lower energy costs, then you have lower hydrogen costs. So the cheaper you can make your renewable energy, the cheaper you can make your hydrogen. Production costs might get to £2 per kilogram or below. Remember, you've got to build one of these plants and you've got to have a return on investment. So, and you've got operating costs of keeping it going. So I'm just guessing at some number around about here. And then I'm guessing again at another number for storage, because you've got these tanks to pay for and to hold, and then you've got to shift the stuff around. And before you know where you are, you're going to have some tax. So it's £10 a kilogram. Maybe it isn't as much as that. Maybe you can get it down to £5 a kilogram, but it's not cheap yet. This isn't free this isn't free power. Quite a long way short of it at present. So what does a green hydrogen future look like then? Well, here are the drivers, the politics, the policy, strategy and plans. The obvious drivers are climate change and decarbonisation. There's also energy security, as we all know about with Ukraine, etc. People are trying to reduce the cost of energy, developing new green technologies to take over from the old-fashioned technologies to create green jobs with the potential for export. And of course, the export gives a potential new public revenue stream, which of course the government's really interested in if they can find something else to tax. And then when you look at something that might be an £80 billion industry within 10 years, there's a lot of investment profits that people are interested in. So there's quite a lot of powerful drivers there. And you say, well, how will the market develop? Well, I don't know. And I think, and I've got a couple of slides that come onto that, but there isn't a market at present. And for a project to be considered bankable, the green hydrogen projects will require to have an association with an offtake contract. And that's with a credit-worthy offtaker. So you can't sell it to somebody unless somebody's going to buy it, and you can't invest in the project unless you've got somebody to buy your product. So there's a quandary that people are going through there as to how to get these very good ideas off. If you had to raise 10 or 20 million pounds to do something, how would you do it? Well, if you're a Scottish and Southern, you can probably do this on your balance sheet. You just take a few tens of millions of pounds when you're operating in the billions of pounds, and build yourself a few pilot projects, and you can fund all that yourself, but and even sell it to yourself if you're if you're making fertiliser, for instance. And will there be a market regulator? This is separate from the health and safety regulator. And these just don't know. All this lot is up for grabs at present. And there's a lot of political strategy planning going on right now, trying to get to grips with that. For instance, there's a publication here, which I cite here, which is the UK strategy, which is actually pretty good. If you read that, you'll see that there is a lot that the UK government has done to think about all these problems already. And they set their ambition of 5 gigawatts by 2050. And I should be able to do the calculation, and I should have done the calculation as to what 5 gigawatts means in hydrogen production, but it's not that much. I think it's less than 1 million tons. It might be something a little bit later on. So this document highlights these barriers: high production and user costs relative to the alternatives, demand uncertainty, policy and regulation uncertainty. People who are investing in this don't know whether they're going to get stuffed by some government regulations. First mover disadvantage. The people invest to begin with, and at relatively high risk, and then other people come along later and take advantage of all their risk. There's still quite a lot of technology uncertainty, investor uncertainty as well. You know, people want to know, back to that previous point about production and demand arrangements. And this last one here, lack of hydrogen distribution and storage. I didn't make these up. These come straight out of the UK strategy document. So, you know, the UK government at least knows what it's facing. And what it proposes is government intervention in helping with all these, which is actually quite good, but it's a strategy and it's not a plan. Scotland's got a strategy as well, which is remarkably similar, but they talk about the 2020s being the demonstration, accelerating market demand and getting the framework right. That's actually really quite that's a bit different from the UK strategy. By the 2030s, they're talking about production at scale, and by 2045, they're talking about global expansion. And they follow that one up with something called a Hydrogen Action Plan, which is at present a draft. And one of the really interesting things in this is this, oops, sorry, I've done it again, is we are committed to a just transmission to net zero, which means working with people, businesses and communities, et cetera, to keep the cost as low as possible, and that the benefits of the transmission are spread fairly. That appears in their document. So they've woken up to the fact that they have to have some sort of democratic accountability and fairness. And they're talking about 5 gigawatts by 2030. And I did do the calculation, that's 0.8 million tons, which is still quite a lot. And 25 gigawatts, which is 4 million tons by 2045. And remember, the EU target was for 10 million tons by 2030. So that's only 10%, that's 10% of the UK market, I mean of the EU market. So you can see that these people are not being completely without an idea, but you know, they're still in that wishy-washy stage between what's a policy and what's a plan. And these are these other strategies. There's the EU strategy, which is published as well. And this is where the 10 million tons by 2030. Oh, sorry, back again. The rest of the world are all at it, especially the renewable energy rich countries like Australia and North Africa, the Middle East, anybody who's got relatively inexpensive renewable energy. And then there's all the vested interests, the oil and gas companies, the power utilities, power trading industry, investment bodies, local government, they're all developing their own strategies. And there is quite a lot of stuff going out there about what people want to do and what they suggest should be done by way of creating a market, etc. And lots of technology companies and consultants and manufacturers, which are all developing their capabilities. And this is growing at an enormous rate. So what might happen in the future? Well, I've got 3 paradigms here, which I suggest, which look a bit similar, but there are subtle differences. In paradigm 1, the big players and the UK government move towards setting up a H2 trading market arrangement, similar to the electricity market. And in that, there are producers. There's a hydrogen grid, similar to the national grid for electricity. There are wholesalers, people who buy from these people. There are retailers who also buy from these people, from the producers. And therefore, there are people who make a living just trading electricity. And their suggestion is that they'll trade hydrogen through these things called hydrogen purchase agreements and carbon offsets. So there could be a whole sort of financial industry developed similar to the electricity industry, all adding cost, of course, to these via these hydrogen purchase agreements or other sorts of wholesaler type agreements. There would also be a safety regulator, likely health and safety executive. There'd be an O2 market regulator. If you had one of these, you'd have to have some sort of market regulation. And is that going to be off-gen, or is it going to be H-gen or something? I don't know, but that doesn't exist yet either. Of course, the Treasury would love to get its hands on this because it's a tax revenue. And there might be some rebates depending on the arrangements. You know, you tax somebody, but somebody else gets a rebate. And these pods, hubs and valleys come into their own, with valleys becoming very significant. In this methodology, you've got to have buyers, and you can't have buyers unless you get valleys. In paradigm 2, this is different. This is where paradigm 1 is considered too difficult because distribution pipeline grid's not feasible, or it's all too long term. So paradigm 2 is more local with ad hoc and direct supply agreements. That is, a particular purchaser, user, signs an agreement to buy hydrogen from a producer or a collection of producers. And so the domestic electricity market then prevails. Oh, sorry, I've done it again. I keep clicking something. And electric cars win out over fuel cell cars, because if you can't get the hydrogen, then electric cars are going to win out over fuel cell cars. You can only move to fuel cell cars if you've got filling stations, and you can't have filling stations unless you've got a distribution network. But in paradigm 2, you get new players rather than the existing big players. New arrangements will come in. There'll be direct agreements created between suppliers and groups of industrial and transport users, possibly with some sort of shared equity in the production, storage, and transportation system. So they're all part of the same scheme. There may be wholesalers in hubs, again with direct agreements, where the wholesalers have a sort of you either buy it or you pay for it. So that might happen. And then there's this Calagas type market for domestic users, delivery by tanker to domestic tanks, which I think has got great legs. But there's still a need for a safety regulator and a market regulator. So this is a different scale of sort of ad hoc development, rather than moving straight to some sort of market mechanism, as in paradigm 1. But of course, you might start with paradigm 2 and eventually finish up at paradigm 1. And then I've got 3, which is a smaller scale again, based on limited domestic market developing. So you're not going to have it in your house, and probably not in your car, because you'll plug into an electric, you'll have a battery and plug into an electric point rather than fill up with hydrogen. But there'll still be deals done for direct industrial power and transport units, and these equity in the dedicated facilities. And the valleys therefore only accommodate industry and wholesalers with these direct supply agreements. There'll be very limited H2 trading outside of the dedicated arrangements, but the Calagas model for domestic users and for local transport might still apply. So you might start with something that looks like this, move on to something that looks like number 2, and eventually finish up at number 1. But it's all too complicated. So I'm coming on towards the end now, which is a point about rural fuel poverty, because I think that hydrogen offers a real opportunity to reduce fuel poverty in rural areas of Scotland and elsewhere. You can get increased community involvement in the pods, and in renewables in general through a community benefit fund which flows from renewable energy development. The current recommended payment from the wind farm developer to a community benefit fund is £5,000 per annum per megawatt of installed capacity. So if you have 50 megawatts of installed capacity, which is a relatively small wind farm, you get £250,000 a year. If it's 100 megawatt, which is a relatively, that's a medium size, a fairly large development, that's £500,000 a year coming in to a community development fund. So that's quite a lot of money that the community have to decide what they're going to do with. And I think that these Calagas type shared services to rural communities in individual or larger shared tanks is a real possibility. So you could have a tank at the end of your drive, if you're or if you're a farmer, you have it behind the sheds, and the tanker comes along, fills you up, and away you go. And you could also have a hydrogen road, which are fuel stations placed at intervals, like the one that we saw that caught fire in Norway. You could have dozens and dozens of those all over the place, and you just come along, fill up, and carry on. And this last bit here, there's an opportunity to make your own. This is a container with an electrolyser unit in. It only uses 25 kilowatts of electricity, and it produces 10 to 12 kilograms of hydrogen per day. So you could have one of these little units stuck on your farm, making your own hydrogen. And as I say here, it's a bit like digging and stacking peat. You know, you make your own. You're an individual or a croft or a few villages together that could have one of these things producing your own hydrogen. All right, so I'm coming towards the end now, which is this stuff is happening very quickly. There's so much going on in the industry now, it's very difficult to keep up, and it's just going to keep getting faster and faster. There are very strong industry pressures because there's lots of money to be made out of this. I think the politicians are slow to keep up because there's actually quite a lot of science in this, and it's not certain what's going to happen. There are lots of technology developments, but some market leaders or some technology leaders are emerging. So if we come back here in 3 or 4 years' time, the politicians might have caught up and the technology might have settled down a bit. Safety regulation is coming along, but it's a big difficulty, especially if you need new legislation, and the whole question of safety standards is very, very difficult for people to develop. And you've only got to get one fire or one explosion, and the whole safety regulation goes into question. I think there's a great danger of getting things wrong in this turmoil. I think that politicians and technologists can take the wrong direction, and I think there'll be some people falling on their face as a result of this. But that shouldn't stop this, because doing nothing will be worse. If you don't get a grip on those drivers of decarbonisation and fuel security, you're stuffed. So you really got to grasp this you've got to grasp this bull by the horns. However, there's a dearth of knowledge in the general community. people don't know anything about hydrogen. It's so new that that most people have no idea of all this stuff that I've been looking at here, and this is only touching the edge of what is out there. So there needs to be major investment in raising public awareness, so that people will be, you can't put a pipeline down somebody's street with hydrogen in it unless you've convinced everybody in that street that it's safe and that it's going to be beneficial. And so it needs an institutional framework to be created and reinforced for Scotland that's proactive and democratically accountable. There is the sort of embryo of an institutional framework coming along, but they haven't got, nobody's yet said, we're going to have a department for hydrogen, and there's going to be a minister for hydrogen development and a staff of appropriately qualified professional civil servants to administer all this. And we're just not going to leave it up to some sort of market model, because otherwise it'll just get wrong in the turmoil. So somebody's got to get hold of this. And I have some, looking at both those UK and the Scottish policy statements, that this is recognised. So, but what they're going to do about it, I have no idea. So that's a lot, I'm afraid. And thank you very much. So I'm open to questions.
Excellent, and thank you, David. And there's though a number of people here, I think, with potential questions. Feel free, everybody, to switch on your microphones, and I'll have a look, and whoever would like to ask is most welcome. In fact, David, you could switch off your shared screen too now. And
oh
then...
no, I was going to go back to to that thing I started with, which is next one down, which was that one.
Okay.
Which was properties of hydrogen, because a lot of potential questions will, I think, probably require me to look at those numbers, because I can't remember them all. There's too many zeros and things in it.
The one advantage if you unshare your screen is I think everybody will see each other. But it's
okay. Okay. If I just do that,
and then you could go back to it. Yeah.
Stop there.
That's it, and you could go back to it there, and that way I can see the faces and the expressions and the signs of a question. I've got one myself, but I think.
Could I ask a couple of questions?
David, yes, indeed.
Around, well, the UK says it's going to try and produce 0.8 million, and the EU says it's going to produce 10 million tons. How does that compare with the current level of green hydrogen production in the EU or the UK? And does either of those numbers have a sort of like a target price attached to it?
The first one is, I don't know exactly how much green hydrogen is produced in the UK or Europe, but it's relatively small. It's in the tens of tons rather than the hundreds of tons or thousands of tons.
Okay.
In the EU, it's much more because they've been doing it for longer. And they use a lot more hydrogen in fuel for cars, but it's nowhere near 10 million tons. It's some very small proportion of that at present. But if we come back next week, it'll have probably trebled. It's moving so quickly. And in terms of cost, there's there's various targets that have been published for reducing the cost of production of green hydrogen. Like the US has got a target of $1 a kilogram, and they think that in renewable energy rich parts of the US, it might be $5 a kilogram now. But I haven't been able to work out what that includes, and whether it includes any transportation costs or any storage costs or any other of the add-ons. Because if you buy petrol, you know, the actual cost of producing the petrol is a small proportion of what you pay at the pump, because everybody's got an add-on. And I suspect that it's probably somewhere around about £10 a kilogram at present. And you might be able to get it down below £5 a kilogram. And I suppose with fair weather and a following wind and cheap renewable energy, it might get below that. But I don't think there's any actual target been set. It would be good to find out if they did.
Okay, thank you.
David, I just wanted to ask you one question. It seemed to me that paradigm 3, as you were leading to smaller and smaller units, could be particularly important for islands, as you would be then deploying their locally produced renewable energy to solve the problem of fuel, which currently in islands is always a difficult one, because in the petrol and diesel distribution system, they're at the end of the line. So were you in that third paradigm particularly thinking of islands and indeed remote and rural areas?
Well, yes, I think that's absolutely the case. I think that that islands are a perfect example of where you could have make it and use it and turn it into some other value-added product that you could send away. I think that's highly probable, especially if you've got places with lots of renewable energy. You know, look at Lewis, for instance. You know, if you were to realize the wind potential of Lewis, it's massive. And a few hydrogen production plants on Lewis and an export terminal and maybe an ammonia factory, and you've just revolutionized the economic potential of Lewis and the other islands. And I think the only ones who've woken up to that really are Shetland, because they've already done it with oil and gas. Orkney is leading, I think, with technology development in these sorts of applications. But I think Shetland's politics are better advanced. And I think the Western Isles are out to lunch at present. They need to wake up, because there's huge potential for them. And you could take some of the rural areas as well. You know, if you went out somewhere on the Ardnamurchan Peninsula, you know, you could have a relatively small scale production of hydrogen that would serve the local community quite well.
And it means that those rural communities then are no longer at the end of the line as regards energy, but they're effectively self-sustaining. In fact, you could almost say future-proof.
Well, I think that if you were building a wind farm, for instance, and this community development fund was to be used so that the community has some potential involvement in the hydrogen development, they could get hydrogen cheaper than anybody else. If you lived out there and you had a hydrogen road, you could have a bus pass equivalent for buying hydrogen. So instead of paying £8 a kilogram, you only pay £5 a kilogram because you're a resident and you own the hydrogen. So although I don't know how they'd work, but there's huge potential for stuff like that to happen. It's all, but that's political, and that and that's how you get the community on board. And as you know, there's quite a large body of resistance to renewable energy developments in general. Wind farms in particular, and not, you could well understood why people don't want to have wind farms in scenic areas, etc. But there's these offshore developments as well. How are they going to, work? What's going to happen to that electricity? And the other one is, if you could collect it and send it to a power station, you might have some balancing of the renewable energy grid. Electricity that's fed into the renewable energy that's fed into the electricity grid is intermittent, and that's why they say they have to have these gas power stations to cover for when the wind's not blowing. Well, if that was a hydrogen power station, that does the same thing. But so all these sorts of things could come along, and I think, along with the Scottish government, that hydrogen for Scotland could be an absolutely fantastic thing.
So you'd almost think like you might say we had a hydroelectric board after the Second World War. We had the Forestry Commission in each case to develop natural resources. Would you say now it's time for a hydrogen development board?
Well, that's my view, but then you see, I was born and brought up in the Socialist Republic of South Yorkshire, so my background is infused with the concept of community involvement in these things, and I think that there's no point in doing it unless you're going to make things better for the people who are involved, and not my friends in Tunbridge Wells. Just a pipeline to Tunbridge Wells or wherever is anathema to me. I mean, they can have a pipeline to Tunbridge Wells when all the people who are directly involved have had their benefit. That's what I think, and not the other way around.
I think Derek would like to make a comment, either make a comment or ask a question. I have that feeling.
No, I was giving David the thumbs up. I think that is absolutely right, and it's the way that we should be going in the future. I think it's just fantastic, and I think this has to get traction. I think David, you have to be in that process as well, speaking to politicians, because politicians aren't experts. I'm afraid the experts they normally speak to are people that have sat in positions of power and have done nothing with it. And so to bring about change, I think they need to speak to people like yourself to bring about the change. And I think, God bless the Socialist Republic of South Yorkshire. That's what I say.
Yeah.
Opportunity for others to come in. We've just a few more minutes and there's time for a couple more questions, a couple more comments.
Yeah, David, you mentioned as an example, €8 a kilo or whatever. Now, what form would that take? Liquid, gas? How much of a tank would you have in your car? And what distance would you get with it? What kind of use would it be?
Well, they're talking about you having one of these super high pressure tanks on your car that would allow you to go about 500 miles. Similar to what you do with petrol. So 1 kilogram of hydrogen is about equivalent to a gallon of petrol, or thereby. So if you were getting 80 miles per gallon, 80 kilometers per gallon, you'd need you'd need 10 kilograms in this tank when you filled up. Unfortunately, the tank itself weighs about 50 kilograms. You know, it's a big, because it's got to resist that massive pressure. And then you've got a fuel cell, which produces electricity, which is relatively small. They've been around for ages. And so that high ratio of fuel of weight of fuel to weight of tank has made people look at only big trucks and buses, where, you know, that weight to fuel ratio makes better sense. So yeah, why would you do it if it's more expensive than electricity or more expensive than petrol? You know, you've got to get it so that it's actually cost competitive. And that's what they've done in Germany with the existing. There are 100 hydrogen fuel stations in Germany. I had no idea that they got as many as that. And there's a hydrogen road that's been around for 10 years in Norway, which is connected up to a hydrogen road going through Scandinavia. So there's probably another 100 fuel stations. But 200 fuel stations is not that many. There'll be thousands and thousands in the UK. But you could imagine it. In one of my slides, I talked about the North Coast 500. It could be the hydrogen North Coast 500. So you have that loop around Scotland with hydrogen filling stations all along it. So I don't know. It's as I said, if you come back tomorrow, it'll all have changed. There'll be more stuff coming out. It's going at an absolutely enormous rate at present. I've never known anything like it.
Ulrich, yes, you just need to unmute Ulrich. That's it.
Does that work?
That's it.
Yes.
You're unmuted.
Okay. I'm always cheeky, and I'm going to be cheeky this time. Thank you, Andy. It's a terrific talk, and I've learned a lot about hydrogen, which I didn't know. My colleagues have been promoting it, and I've been contradicting them because solar panels and electricity are so good. Why bother? But you've convinced me there is something to bother about. So terrific. Thank you. There's just one thing I want to question, and I question all of these technologies for that. We've achieved a fantastic level of success with petrol and transport and all the things we do. And I don't see why we have to try and repeat that. If it's not as good as the existing petrol, tough. And put it the other way, suppose we didn't have any of those things. We were at the horse and cart stage, and this came along and was being developed, and it didn't do all that the petrol thing did, but it did quite a lot, as you've described. That would be good enough. You know, just because we've been spoilt for a couple of centuries, not even, doesn't mean we have to go on the same path. So I just wondered whether anybody actually has comments there. Why should we do what we've learned to take for granted wrongly?
Well, Ulrich, I completely agree with you on that point. I think that you're absolutely right, because there are these very strong vested interests that would like to replicate something like the oil and gas and the power industry. And it seems to me that there are just too many unnecessary parts to that industry, and that there is no reason why we need to try and do the same thing again. So my paradigm 1 is the replication of that, and my paradigm 3 is something less than that, that might still be good enough. Right. And so I agree with you. I think we should only do something that's good enough.
Yeah.
And not, but of course, you know, if you're the managing director of Shell, and you say, well, what's going to happen to me when, you know, what's going to happen to my industry if I don't get involved in this stuff? We're stuffed. What's going to happen to my investors? And they're all, those powers are just enormous.
Only a very stupid animal would follow a vested interest. You know, it's really, vested interests are at a fundamental level of no importance whatever. In practice, we're tied up with them and we're absolutely stuck. But that's a crazy situation to be in. So I don't myself have any sympathy for vested interests. But you know, if they persevere in that, they're wrecking the world. That won't do.
Well, it's also very complicated because the vested interests have got investors, which are you and me, through our pension funds and through goodness knows what else.
Absolutely, it's a huge tangled bureaucracy.
It is. Yes. It's just a complete tangled web.
Yeah.
And you know how the new market develops, how the new hydrogen industry develops. It doesn't necessarily have to follow the previous model. It could follow something that's a lot more organic and a lot more local and a lot more needs-based. But I don't have any great confidence that that will work, because I think that the vested interests, being as they are very likely to have a very strong influence on everything.
Do you know of that little car manufacturer in Wales? I think he's called Swales, is he, or something like that, who makes a fuel cell car which works on hydrogen, exactly like you described. The whole car weighs about the same, he said, as a Tesla car battery. So it's very light in plastic, and it's built on a different economic model. You never own the car, you only hire it, and it's fully serviced for you, therefore. And as bits fall off or it decays or the whole thing has to be chucked, the whole of it is given back to the manufacturer of those parts, and they remanufacture from the scrap. So the whole thing is completely changed. I've forgotten the name of the company, but they are actually working to produce the first ones. Do you happen to know that?
Tesla. 20 years ago,
it's another way of getting in through the economic system and the vested interests. You short circuit them. Yeah, sorry, I interrupted you just to make that point.
No, what I was saying was just look at the worldwide success of Tesla that's come from nowhere, somewhere, by embracing a particular technology, and now they're a major manufacturer, and everybody else is copying them. So I don't see why somebody like this Swales car or whatever they're called cannot do the same thing.
Well, they're doing it completely differently under a way that gets over some of the problems you've highlighted. Yeah. Okay, they're worth looking into.
This has been a very interesting discussion indeed, with some really fresh ideas. And indeed, I think that car would be interesting to hear more about. Ulrich, that's something, if you email me, I could always circulate people. And I think it's credit to that fascinating presentation by David that he stimulated so much interesting discussion and debate. We are delighted with the way the series is going. We're going to take a break in July and August, and then come back again at the end of September and continue right through the winter and into the spring, because there's lots more good ideas have been coming up. So in the meantime, all that it remains for me to do is to thank everybody for coming along and joining in. And David, well done indeed.
Thank you.